Hi, this is a tutorial which shows you our Affinity software flow together with the TI-60 eval board tutorial. I'm using the software 2021.2. To show the flow, we have a simple up counter written in VHDL with 3 inputs, ZN, stop N, both are low active, and the CLK in with a 25 MHz clock. And we have 6 outputs. The lower 3-bit are connected to an RGB LED and the upper 3-bit are connected to an RGB LED. Means the lower bit will change the color much faster on the LED and the upper bit slower than the other one. So connections from the IOs will be done to the boards. For example, our ZN will be connected via the package pin C5 to the switch 7 on the board. The stop N pin will be connected via the K13 pin to the switch 5 of the board. The CLK in will come via the B2 package pin and is a 25 MHz clock. And the LED outputs will go to the 2 RGB LEDs. The lower bits go to blue, red, and green, K14, J15, H10. And the upper bits going to blue, red, and green, J14, H15, H11. And then connected to the D17 of the RGB LED. Means the lower RGB LED will change the color faster than the upper one, the D17. Now we are going to start our software. To do this, I will switch directly to our software. I start the Affinity software. I'm using the Affinity software 2021.2. We open the project, go to the project directory, open the new project XML file. Now the tool is loading the project information. What we are going to deliver is a counter.vhd file, the test bench VHD file, the counter constraint where we add the SDC file to constrain the whole design. And the information are stored in the new project XML file. In addition, we are providing the whole project with all the connections. And this is stored in the TI-60 eval board solution.zip file. We are providing the user guide of our eval board and this lab, which goes through the flow step by step. So going back to the software, now this project is loaded. We can double click on the counter.vhd file, where we see the VHDL file with a CLK25 signal. This is coming from an internal PLL, which is generating at 25 MHz. The locked signal, the reset signal, the ZN and stop N signal, and the LED output, 6-bit output. And here you can see that we are connecting the upper bits from the 30-bit counter to the LEDs. To start this, we can as well edit the project settings. Here you see we can select the device TI-60F25. We can select the speed grade, the C4, the C3, or the industrial device. So we stay, for example, with the C4. Then the design. Usually you have several VHDL files, or you can have as well a mix between VHDL and Verilog file. Therefore, you should provide the top module or entity name. Here in our case, it's counter. The entity name is counter from the top module. Therefore, we are providing the name as well here as top name. For VHDL, we have the possibility to change between VHDL 1993 or VHDL 2008. Default is VHDL 2008. But if you have older VHDL files which are designed in VHDL 1993, then you can switch this as well, because they are not 100% compatible. So in VHDL 2008, there's slightly some stuff different. If you would like to work as well with different libraries, you can change here as well the library name to a new name. Therefore, you can add a new library name, type in the name, and assign it to your VHDL file. Here you have some possibilities for synthesis setting. We keep this as default, and here as well some possibilities for the place and route. So this makes sense if you need to do some timing closure, then you can play around with synthesis options, with place and routes options. Here we have as well the bitstream generation. You can select active and passive mode, and as well where the clock is coming from the internal oscillator, or you are providing a faster external clock. And then here you can set all the dividers. The fastest is diff by 1, and diff by 8, it's the slowest internal clock divider. And here you can set as well the other settings as well if you would like to do an encryption and as well authentication. But this will not be covered in this tutorial. So now we set up our project. Now we go to the dashboard. Here we can select our automated flow. I think for the beginning we can start just with the synthesis, so it should not go through the whole flow because we have not assigned yet the pin names. Therefore, having a successful synthesis is very useful. Here we can see we are needing 49 lookup table and 36 flip-flops for the whole design. See this as well here in our reports. You can open as well here the CSV file, and you see, okay, we are using 36 flip-flops and 49 LUTs. This is a useful information if you have a larger design, then you see all the modules with a related resource usage. Now we can go back to our project and open the counter constraint.sdc file. Here you can constrain your design with standard SDC commands. Here for example, we have create clock -period 40, CLK 25 means we have 40 nanoseconds, which is equivalent to the 25 megahertz clock we are providing. So the next step is now that we assigning the pins to our interface. Therefore, we are starting the interface designer. The interface designer, we are doing the connection from the signals to the package pins from the FPGA, as well the PLL configuration. Here, the interface designer shows us, okay, we have the TI-60F225 silicon. We see we have GPIOs, we have the PLL, we have an internal oscillator, we have the LVDS RX-TX pins or bidirectional LVDS pins, and as well the MIPI lanes and the JTAG interface. To start the stuff, we're going to GPIO. And first, I think we would like to assign the LED pins. And the LEDs is a bus to create bus. The name is LED. And it's a 6-bit bus. Therefore, the upper bit is 5. The lower bit is 0. It's an output, and we stay at the 1.8 volt LV-CMOS. Going next, the pin name is LED. I think we can change the drive strength from 4 to 16 milliamps. We can as well change the slew rate if we want. We go next, then we get the overview about our settings and say finished. Now we have an LED connection, and here you have to be careful. You have to be case sensitive. Even if you are using VHDL, you have to be case sensitive. That means if you have a capital letter LED in your VHDL file, you should have as well a capital letter LED here in the interface designer. After assigning the LED pins, we have additional pins. We have 3 input pins. Going to GPIO, and now we can add blocks. And we have 3 additional pins. We're doing this 3 times. So now we have additional 3 input pins. Before we change the name here, we go back to the LEDs and go to the resource manager. And now we see our defined pins. And now we can assign them to the package. For example, starting with LED 0. And if you look to your PDF file or in your VHDL file, you will see that the LED 0 should be connected to K14. So now we are looking for K14. It's here. And press return. Then all the other stuff will be filled up. You can assign as well via here the GPIO information. Then you assign it to the internal physical placement and not to the package pin. So it depends what you prefer. Then the LED 1 should be connected to J15. J15. Press return. The LED 2 should be connected to H10. H10, always press return. The LED 3 should be connected to J14. And the LED 4 to H15. And the last one, the LED 5, should be connected to H11. Return. Now we have not assigned the names here for the GPIOs. Therefore, we can go back to our Design Explorer and we can now change the names, for example, to the Inst7. The first signal, I think we go to select the Inst7, change the name to Stop N. As well here, be careful, should be case sensitive. And after typing it in, press return, because otherwise this will not be saved to your stuff. And you see here, no longer the GPIO Inst7. Now you see Stop N. Now you can configure the Stop N. Sure, it's an input. We stay at 1.8 volt. And here you can configure the pin in addition if you use an additional register. And here you can select the pull mode. And for example, we can here add a weak pull up to this I/O pin. The same now for the next one. Select GPIO Inst8. This should be selected to the ZN. Return. It's as well in input mode. We select a weak pull up for this. And then we can go to the last one. Select GPIO Inst9. And this is our CLK in. Return. And the mode is input, input setting, the connection type. And this is no different to the other one because this is used as an PLL input clock. Therefore, we are using PLL under CLK in. So now we defined our three pins. Before we're going to assign these to the I/O pins, we are adding a PLL to the design. We are selecting the PLL, right mouse button, create block. And now we added a PLL to our design. Now we are going to configure it. Therefore, we can go to the block editor. First, we assign the location. So we are using the PLL top left 0. It's an external clock source, so we can use as well signals from an internal FPGA or dynamically. So we have a clock max at the beginning, and then you can select dynamically which clock should be used. In our case, we are using external pin. Here then we get the information where this pin should be assigned to. It's GPIO L18. Configure the PLL. We are starting the automated clock calculation. We have here the input pin. So we know it's a 25 megahertz clock. This is fine. Then we go to the output clock. It should be as well a 25 megahertz clock. So we can change it to a different number, but keep it simple. We just show the selected stuff. The output clock name should be CLK25. We would like to have a reset pin. And this is called PLL under reset N because it's low active. And then we would have to have a locked pin to see when the PLL is locked. So always click on the cross here. Therefore, you can enable it. And the locked pin should be called PLL_locked. So you can as well do all this stuff in a manual setting. So switching to the manual mode, you can change as well the pre-divider, the multiplier, the post-divider, and here the clock divider, and as well the phase shift stuff. But keep it simple, we stay in the automatic mode. And now we say finish. So with this step, you defined your PLL. So if you need more outputs, you can add this as well. And you can change as well the different feedback modes. Now coming back to our resource assignment, we start directly with our CLK in. We go to the package pin, and this should come via B2. And if you remember from our PLL, the input pin from our PLL is GPIO-LP18. GPIO-LP18. So we choose the right CLK pin to this. The next one is stop N. This is connected to K13. K13 and return. And our last one is ZN. And this pin is connected to C5. Go to C5 and press return. So now we assign all entity IOs to our BGA balls. And after this, we can check the design. Check the design has now some design rules, check in the background, and we'll check against these design rules. As we defined a PLL, we can as well generate constraint file automatically. So for this, it's not a big deal because it's one PLL. But if you instantiate several PLLs with different clocks, you can make your life easier. Just generate the PLLs or the constraints file, and this will be automatically go to our design structure. So now we checked it, it's saved automatically, and we generated the SDC file. Closing this file, if you now go to the result interface designer, here is a SDC file, and here is the SDC constraints automatically generated, and now you can copy all these settings and place it to your project file, SDC file. So now we have the SDC file, we have the assignment, and now you can go back to your dashboard, go back now to the automatic mode, and run here, place and route. So they are not doing the synthesis anymore because we do not change the VHDL file. Therefore, the tools know that he only has to do the placement and the routing and will go to the bits file generation. So this will take a bit of time. In the meantime, you can already connect your eval board to your USB connector. So to prepare the programming, you have to install the driver for our Titanium TI-60 eval board. And this you can do with the SADIC tool. Start the SADIC tool and click on List All Devices. Then choose the Titanium TI-60 development kit and assign the lib USB-K driver to this board. Click on Replace Driver, and then the driver is set. You should do this for interface 0 and interface 1. Please do not use it for interface 2 or 3. Going back to the software, they are now generating the hex file and the bit file. The generated hex file you can use to program the SPI flash. The generated bit file you can use for programming the SRAM layer via a JTAG connection. So the design flow is finished. What you can do next is checking the routing and checking the timings. This is important that you always check the timing if the design meets your timing requirements. So this is our constraints, 40 nanoseconds or 25 megahertz. So the constraint will show us that you can run the whole counter up to 674 megahertz. So timing is okay. Now you can go to program the bitstream to the FPGA. Therefore, you can start the programmer, or you can go here to Tools, Open Programmer. So as we already connected the TI-60 board, the USB target is shown. If this target is not shown, redo the driver installation, because then something was wrong. So now we can select the bit file because we are choosing the JTAG because it's faster than the SPI. So, but you can use both. So, but if you would like to program the SPI flash, you have to use hex file. JTAG, here you see the device select and the JTAG clock speed. We leave it at 6 megahertz, but here you can change it as well to 15 megahertz if you would have a faster transfer. Then click to this play button, and now the design is passed via JTAG to our FPGA. And if you look to your board, now the RGB LEDs are changing the color. One of the lower one is changing the color much faster than the upper one, because the upper one is connected to the upper bits of a counter. Therefore, this will be much slower than expected. Okay, this was everything. Goes from design entry to pin assignment, PLL configuration, and bitstream generation, as well to programming our eval board. You will find additional information about our software on our web. If you go to Software Affinity IDE, we have additional videos here which shows in detail how to create an LVDS block or DDR memory interface and so on. Thanks for your time, and if you have questions, feel free to contact Evenix. Bye.